These components are part of one of the first Galileo satellites. Galileo will consist of a constellation of 30 satellites orbiting about 24,000 kilometers above the Earth and providing a true network of coverage. But before this full deployment, a testbed phase is necessary.
Thank you.
This involves the launch of an experimental satellite whose purpose is to test the technology and also to secure the frequencies agreed with the ITU, the International Telecommunications Union. Under ITU regulations, the Galileo satellite will have 2 satellites being developed in parallel to guarantee a successful mission. The program will then undertake its in-orbit validation phase. For this step, a contract worth 150 million euros was signed between ESA and Galileo Industries. The in-orbit validation phase consists of a mini constellation of 4 satellites with associated ground stations, demonstrating the concept of the system. Thereafter, the remaining 26 satellites are launched. As Galileo is being built step by step, the ESA is having to deal with many technical innovations. All forms of transport, whether road, rail, air or sea, will benefit from Galileo. It will improve search and rescue operations and open the way for applications in many different situations. With Galileo, Europe is equipping itself with a system offering worldwide availability. Furthermore, unlike American GPS, its civilian character will be a guarantee of continuity of access and signal quality. Galileo, therefore, has many different sides, which makes it a very challenging program. To provide a navigation service until Galileo becomes operational, Europe has already started putting a system in place. EGNOS, the European Geostationary Navigation Overlay System. This is a network of ground-based stations which analyze GPS signals, process and improve them before retransmitting via geostationary satellites, a GPS-type signal with an accuracy down to 1 meter. This service is initially intended for air traffic safety, for non-safety of life applications, and certification processes for safety of life services such as landing planes. EGNOS will pave the way for Galileo and will mark a revolution in our daily lives and will also ensure Europe's independence through a major civil industrial achievement. What caused a planet like Earth to form around our Sun? What made chemicals burst forth into life? And how did life form? Astronomers are studying celestial fossils from the solar system's earliest times to try and help answer these questions. It is thought that planets and the Sun were created 4.5 billion years ago. Made from clouds of gas and dust, they were swept clean by solar winds and heat from the Sun. Further away from the Sun, planets such as Jupiter and Saturn were preserved as giant gas balls. Comets, however, remain as frozen fossils, believed to hold the secret of the chemical makeup of the solar system's birth. So far, we are aware only of life here on Earth, but clues to its origin can be found in the distant reaches of the solar system. NASA has several missions to the outer solar system to try and explore the furthest reaches. One of the missions is Cassini.
Comets in the outer solar system are probably composed of the same primitive chemicals as the ancient nebula of gas and dust that formed the Sun. In 1986, a fleet of international spacecraft tracked Halley's Comet and revealed a snowball of dust and ice, and the hint of organic compounds. In 1995, Kraft was launched to a typical comet named Koph. On its outward flight, the spacecraft first investigated an asteroid, and in August 2000, it reached its destination. As Kraft travels alongside the comet, it fires a penetrator lander equipped with a laboratory of instruments. These instruments are designed to sample chemicals that could be relics of an era billions of years old. Cassini is an international mission that combines an orbiter spacecraft built by NASA with a probe provided by the European Space Agency. Cassini was named for the 17th century astronomer Jean-Dominique Cassini. The spacecraft Cassini will orbit Saturn for at least 3 years, giving scientists an extended look at the ringed planet and its elaborate system of moons. Here in the Paris Observatory, Cassini discovered 4 of Saturn's moons and the division in the planet's rings. The most tantalizing of the moons is Saturn's largest, Titan. Titan is larger than the planet Mercury and is the only moon we know with a major atmosphere. On arriving in the Saturnian region, Cassini will launch its European-built probe to descend to Titan. The probe will measure very complex molecules which are expected to be found in the atmosphere. It is hoped that the detailed measurements will confirm Titan does indeed have a thick nitrogen-methane atmosphere, the chemical precursors to a life-supporting environment. It is possible that huge lakes of liquid methane and ethane exist on Titan. The probe will also analyze compounds on the surface and relay the information back to the orbiting spacecraft and then to Earth. By exploring the comets, asteroids, Saturn and its moons, we are looking back in time in a quest that will help tell us about our distant beginnings. This is the astronomical equivalent of being the first to open an ancient vault.
British chemical scientists say extraterrestrial molecules found in meteorites may hold one of the keys to the origin of life on Earth. This research was inspired by a 1992 account identifying a type of phosphorus called phosphonates in a meteorite which crashed on Earth. It confirmed that these had been created in interstellar space. Meteorite activity and the components and structure of meteors and comets remain of great interest. Teams at Leeds and Bradford universities are trying to reproduce the exotic molecules of these systems. The aim is to provide the first direct chemical link between phosphorus compounds found within interstellar gas clouds and those incorporated within solar system meteorites. At one level, the work is providing more and more knowledge about meteors and their connection with Earth. At another level, this work could just provide a major clue, possibly a link to the origin of life on this planet. This is the Yuri Gagarin Hydrolab Cosmonaut Training Center, better known as Star City, some 40 kilometers from Moscow. Cosmonaut Dmitry Verba dons the Orlan spacesuit. Dutch astronaut André Kuipers is also being kitted out. These two are carrying out a series of underwater tests on the European robotic arm, known as ERA. This robotic arm will assist with a new Russian module to be added to the International Space Station. It's Cooper's turn to get into the 250-kilo suit. He's an experienced astronaut, once spending 10 days on the International Space Station. The astronauts begin their practice drill on the European robotic arm. ERA was due to go to the International Space Station in 2001. But there has been a series of delays, including the Columbia Space Shuttle tragedy in 2003. Hank Peterson from Dutch Space says ERA's mobility will be the key to its success. The tank gives close to ideal conditions for the astronauts to practice assembling ERA, as they will have to do when they arrive at the ISS. The exercise lasts a grueling 3 hours, but they've achieved their goal, which is to familiarize themselves with every nut and bolt on the arm. The testing has been successful despite a number of minor glitches. Those inside the control room are pleased. The International Space Station is already equipped with a Canadian-built robotic arm some 17 meters in length and a mobile servicing system. ERA's mobility will complement it. Being several meters underwater gives similar visibility to being deep in space. Limited vision is one of the problems, as is handling delicate tools while wearing gloves. But at least, says André, the suit fits fine. Home thoughts from abroad are rare when you're just getting the job done. André's final word on the fantastic task ahead? If you're busy, you don't look at the Earth at all. I know from my colleagues that you're just busy with your task. These grainy pictures are a breakthrough in space science. They were taken 3.2 billion miles away on Titan, Saturn's largest moon. The images were transmitted from the Huygens probe, which landed on Titan after a 20-day journey. This project took 7 years, and now scientists can really start to understand what is out there as the information filters back. They're hoping to learn more about the origins of life on our own planet. Titan's atmosphere is believed to resemble Earth's, as it was 4 billion years ago before life began. As more images reveal the true nature of Titan's surface, scientists around the world will build up a picture of a moon that previously was a total mystery. On some space missions, simple experiments were done to prove or demonstrate the physical behavior of objects in zero gravity. Here we launch a Gravitron to float freely in the cabin. It wants to spin about the wheel inside. To try and get it to tip over, the astronaut bumps it on the top and on the side, but it won't capsize. It's stable about the spin axis in which it was released. That's straight up and down. Here is the same configuration, one spinning Gravitron, but this time it's been oriented so the spin axis is pointing at the camera. Again, although it's been bumped on all sides, it will not tip. As before, it's stable about the spin axis in which it was released. This is a graphic illustration of the difference between a spinning and a non-spinning Gravitron. You'll notice the spinning Gravitron remains stable, whilst the other one tends to tumble end over end because it has no stable spin axis. If we watch it one more time, you'll see that one is spinning and one is not. The one that is not spinning just tumbles free, while the other one maintains the orientation in which it was let go. Now two spinning Gravitrons which are both stable as they spin. If we take one and bounce it off the other, you'll see that this time, because they're both stable, neither tumbles after they collide. Now a curious combination. Two Gravitrons attached together on a wiffle ball. They're both spinning in the same direction, so one would think they would be very stable in this configuration. But because they weren't perfectly aligned with each other, they got out of hand. Eventually, disastrous results. In slow motion, you can see how the misalignment causes them to break apart. But this time, the two Gravitrons are rotating in opposite directions from each other. And because their angular momentum vectors are in opposite directions, their stability axes cancel each other. So in theory, when we let the device go, it should tumble. Obviously, we can't make them both spin at exactly the same speed, so one of them is going to have a little bit of stability. But now we can bump the stack and make it wobble a little bit. As we bump it more severely, there is some tendency for stability, but not as much as a single Gravitron had floating on its own. So clearly, two Gravitrons spinning in opposite directions cancel each other. Now we're getting complicated. We have three Gravitrons all hooked up to the same wiffle ball. They're orthogonal to each other. That's to say, they're all at 90 degrees to each other. And this time, we're going to spin them all in the same direction with reference to their attachment to the wiffle ball. As we do this, you would expect the angular momentum vectors of each of the Gravitrons would add up to a single vector, which would be right between all three. As we release the device, you can see that the only axis it will rotate around is an axis that you could see if you put a pencil between all three of the Gravitrons. That is, an axis that is equidistant from all three of them. As it continues to spin up, by the natural character of the friction of the Gravitrons, it eventually begins to spin so fast that it comes apart. Here is the same combination again. Three Gravitrons mounted orthogonally to the wiffle ball. Once again, we're going to spin them all in the same direction. But before we do so, you can see how they tumble end over end. There's no stability there because none of them are rotating. Once the astronaut sets the Gravitron spinning, you'll notice that initially they begin to rotate around the same axis as before. But one of the Gravitrons comes off. And look what happens to the remaining two. They begin to rotate around a new axis, one that's right between the two. Again, they spin at such a speed that eventually the device falls apart. Here's an experiment that demonstrates how a non-spinning Gravitron behaves just like a ball on the end of a string. We can change the axis of rotation just as we could with anything attached to a string on Earth. But once we spin the Gravitron up, look how it maintains that stability around its rotation axis. We can spin it around and around, and it wants to stay in an orientation so that the spin axis is parallel to the axis of rotation to which the astronaut is holding the string. But when we changed the orientation, eventually the Gravitron ended up changing the orientation of its rotation so that it matched the rotation axis of the string. This shows in a simple way how gyroscopes work. No one knows for sure just how much matter or even how many planets exist within our solar system. Since the discovery of the distant Pluto in the 1930s, astronomers have searched for the traces of planets even further out. Then in 2003, Hubble spotted something moving fast enough across the background of faraway stars to be an object within the solar system. The object, later named Sedna, is about 3/4 the size of Pluto. It is so distant and so small compared to most planets that even to Hubble's sensitive cameras, it only appears as a speck of light. Sedna is the largest planet-like object discovered in the solar system since Pluto. Given the vast number of stars that exist, it's certain that some of those planets that have been discovered, called extrasolar planets, are capable of supporting extraterrestrial life. Using the Hubble, astronomers have been searching for planetary systems like ours orbiting other stars in our galaxy. Analysis of the light from the planet's clouds that Hubble has discovered enabled the astronomers to partly determine the chemistry of its atmosphere. They're looking for chemical traces that could be the result of living organisms in the way that oxygen on Earth is created by plants. Signs of chemicals like oxygen or methane in the atmosphere around extrasolar planets may be signposts to the discovery of life beyond our solar system. In the end, it wasn't much of a contest. Panna Felsen, a high school student, was pitted against a succession of robotic arms in front of an audience of NASA engineers. But this wasn't for fun. NASA billed it as a serious demonstration of robotic capabilities. Well, so much for that one. It's back to the drawing board for its designers, who seem puzzled by the ease with which it was beaten. Here's another robotic contender that was pitted against the new champion. This time, it's a bit more of a challenge for Panna, who nevertheless prevailed, in spite of the robot designer offering a helpful hand to his charge. But NASA engineers are undaunted and proud of their progress. They have summoned a new era of possibilities that they couldn't do before. Imagine if it was possible to make robots that run like a cheetah on Mars. This isn't a cheetah, but a prototype of the sort of robots that will one day work on Mars. And here's a robot arm and hand, sensitive enough to pick up a nut or a screw. Attached to a robotic body, it could help construct buildings on other planets. But back to the arm wrestling contest and the third challenger. Well, maybe next year. Parallel to guarantee a successful mission. The program will then undertake its in-orbit validation phase. For this step, a contract worth 150 million euros was signed between ESA and Galileo Industries. The in-orbit validation phase consists of a mini constellation of 4 satellites with associated ground stations, demonstrating the concept of the system. Thereafter, the remaining 26 satellites are launched. It will consist of a constellation of 30 satellites orbiting about 24,000 kilometers above the Earth and providing a true network of coverage. But before this full deployment, a testbed phase is necessary.
Oh, thank you.
This involves the launch of an experimental satellite whose purpose is to test the technology and also to secure the frequencies agreed with the ITU, the International Telecommunications Union. Under ITU regulations, the Galileo satellite will have 2 satellites being developed in parallel. These components are part of one of the first Galileo satellites. As Galileo is being built step by step, the ESA is having to deal with many technical innovations. All forms of transport, whether road, rail, air or sea, will benefit from Galileo. It will improve search and rescue operations and open the way for applications in many different situations. With Galileo, Europe is equipping itself with a system offering worldwide availability. Furthermore, unlike American GPS, its civilian character will be a guarantee of continuity of access and signal quality. Galileo, therefore, has many different sides, which makes it a very challenging program. To provide a navigation service until Galileo becomes operational, Europe has already started putting a system in place. EGNOS, the European Geostationary Navigation Overlay System. This is a network of ground-based stations which analyze GPS signals, process and improve them before retransmitting